Have you ever looked closely at a garden and wondered why a snail inches across a leaf while an empty shell just sits there? That difference comes down to the most basic rule of nature, sorting things into living and non-living. Living things breathe, they move on their own, and over time, they grow. If you place a seed and a piece of paper in wet soil and wait a few days, the seed will push a green shoot up through the dirt. The paper does nothing. Growth is a clear signature of life. Plants are incredible because they can actually build their own food from scratch, using nothing but sunlight. This self-sustaining way of living is called autotrophic nutrition. Since we can't create energy from the sun ourselves, we have to eat other organisms, like that plant, to survive. Because we depend on others for energy, our way of eating is called heterotrophic nutrition. To keep our bodies running, we need a specific mix of these absorbed nutrients, which we call a balanced diet. We need carbohydrates and fats for fuel to move, proteins to build our muscles, and vitamins and minerals to protect our immune systems. So when we observe the world around us, life begins with those simple actions, moving and growing. And every bit of that activity depends entirely on how an organism sources its energy. Let's zoom in on something simpler than food. Take a glass of water. Everything you can touch, taste, or see is made of matter. And if you zoom in close enough, you will see that matter is built from microscopic puzzle pieces called particles. This chart categorizes those pieces by complexity. The purest substance is an element, and its smallest uncuttable unit is an atom. When atoms group together, they form a molecule. When different elements lock together in a specific fixed recipe, they form a compound. Here is an animation showing what happens when different compounds mix without locking into a new recipe. If you stir salt into water, the salt spreads out so evenly that the mixture looks like one single clear liquid. We call this a homogeneous mixture, or a solution. In this mix, the water is doing the heavy lifting by pulling the salt apart. We call the liquid doing the work the solvent. The salt being broken down and dispersed is the solute. But not everything plays so nicely. If you stir some sand into that same water, the grains never fully dissolve, remaining distinctly separate. This is a heterogeneous mixture. Look at this photograph comparing the two. On the left, you see the clear, homogeneous salt water. On the right, the muddy, heterogeneous mixture of sand and water, where the grains simply sink to the bottom. Whether you're looking at a glass of water, your dinner, or a rock, the incredible variety that we see in our world is just the result of how these invisible particles interact and mix. Those vibrating particles are constantly in motion. When we add heat, they bounce around much faster, eventually breaking free and sliding past each other as a liquid, or even flying off as a gas. This is how matter transitions between states. Matter also dictates how light travels through an object. Materials can let all light pass through, block some of it, or stop it entirely. Look at this grid. The clear glass on the far left is transparent. We see straight through it. The frosted butter paper is translucent, letting only a soft glow pass. And the wooden board on the bottom right is entirely opaque, blocking light completely. When matter changes shape or state, like that ice melting, it is undergoing a physical change. The water looks different, but it remains exactly the same substance. If you leave a glass of milk out on a warm day, it turns sour and thickens into curd. That is a chemical change. The particles have reorganized themselves to create an entirely new substance with a new set of rules. Because we know how these properties work, we can reverse certain mixtures. We can filter sand out of water, pick pebbles out of rice by hand, or even use a magnet to pull iron filings out of dirt. By recognizing whether a specific substance is a solid or a gas, how it handles light, and how its chemicals react, we gain the ability to safely navigate and shape our physical environment. To study all this life and matter accurately, simply observing it isn't enough. We need a shared language to measure it. In science, we use systems called physical quantities. This chart shows how we map fundamental physical quantities to their units. When we measure the distance or length of an object, we use meters. When we measure its mass, we use kilograms. For tracking time, the standard is the second. And to measure temperature or heat energy, we use Kelvin. We started by looking at a snail to understand the basic requirements of life, zoomed in to a glass of water to see the invisible particles that build our world, and ended with the precise tools we use to measure them. Now let's put that understanding to the test. Pause the video here and take a moment to answer these questions. Every day, we use the logic of science as a practical toolkit to decode the reality happening right in front of us.